preparing for the symposium, I really forgot about my own paper and just to make presentation file, and also maybe struggling to recollect details in this paper, but I'll try. And I'll talk about this topic of sustainable urban growth in particular complexity, kind of standard topic in the area of sustainable development. Well, this study has started from the reflection on the fact that population density is a measure that is too, in my opinion, overused in the discourse of complexity, discourse on complexity. For instance, Newman argued that surprisingly, researchers and practitioners have only recently begun to rigorously define complexity apart from density. Well, in line with these recent efforts, first Hillier has suggested the idea of spatial sustainability. He said a city can be made more sustainable by the reorganization of its street network through the process called local grid intensification in the center, since it is capable of enhancing the general accessibility within the city and thus reducing the energy consumption required for vehicle movements. Well, but he didn't take care very much of building distribution. Well, I mean, height distribution in the city. On the other hand, there's a Ratti who said the spatial form of the cities alone, apart from building design, system efficiency, and occupant lifestyle, may account for up to 2 times variation in energy consumption, if not by reducing movements by cars, but by increasing passengers, the naturally lit and ventilated buildings in individual buildings. But he disregarded the so-called network effects, which we take care very much. Right. The aim of this research is to consolidate the idea of spatial sustainability by combining the configuration both of the street network and building assets. For instance, when Hillier said local grid intensification in the center, it can be symbolized as the far left side figure. The grid is small and dense in the center of the city, while in the opposite direction we can have this kind of diagram showing local grid intensification in the periphery, which we do not find very often in real cities. And what I want to do is that what happens if we put buildings with different heights in this gridded layout, and what will they have in terms of configuration effects to all the buildings or all the movements. And in particular, we aim to develop a quantitative model to estimate the amount of carbon emission which is affected by movement within buildings and between buildings. Therefore, to make possible comparative morphological studies by taking the amount of carbon emission as a kind of single currency. This is a model description. Well, I have to make a warning, a little bit warning. There will be a little bit of mathematical, but it's kind of very simple, but you don't have to worry too much about it. And it starts from like this. Suppose a single movement, or you may call it a trip between 2 buildings, I and J, and movement consists of 2 parts. Horizontal movement by car between buildings, and vertical movement by elevator within buildings. Okay. For horizontal movement, we define shortest path distance between the 2 points on the street, which are closest to the centroid of building footprint. A bit technical, but this is our assumption for the horizontal distance. And for the vertical distance, I will suggest the idea of effective height, which is defined as the half of vertical distance above the 3rd floor plus the height of 3 floors. It's kind of a way of averaging the height of different buildings. And then I will suppose that this movement, single movement, generates carbon emission while we are using elevator will consume electricity. Then it can be converted into carbon emission amount. Right. Carbon emission, CIJ, means carbon emission between that why we are moving from I to J is composed of 3 parts. We should go down within the building at the origin, and we should move between the buildings, and we should go up using an elevator at the destination. And there is a height and distance, and we multiply the unit amount of carbon emission at each part to estimate the amount of carbon emission. And then we assume that movements are generated in proportion to the population of the origin and the total floor space of the destination. So for instance, if the total floor space at the destination, the ratio of these and these is, for instance, 7 to 3, for instance, then the population here at the origin will be divided into this destination according to that ratio, 7 to 3. And also we assume that the population at the origin is also proportional to its total floor space, but this is typical assumption in kind of traffic engineering field. So we have the equation for movement, amount of movement, I would say, from I to J, which is proportional to the product of floor space of origin and destination. Right. And the total amount of carbon emission produced by those multiple movements between 2 buildings becomes then just multiply the unit amount and the total amount of movements there. And we sum them, sum these values relative to the origin to have the carbon emission potential of the individual building. So we have just one subscript here. And now we sum again these values over all buildings in area to have the total amount of carbon emission in a city. So we don't have a subscript in this equation. And divide this total amount by population, we can have the amount of carbon emission per capita. Right. For simplicity, we will assume that this is, kind of parameter for the distance and distance and height, right? Elevator and cars. We assume that they are all global parameters, meaning that they remain invariant for all places and all types of elevators and cars. In that regime, we estimate from the data that, well, the unit amount of carbon emission for elevator is 611 grams CO2 per kilometer. On the other hand, car, we have 239 grams CO2 per kilometer, which is far less smaller than elevator. This is the rare case, but in real cities, elevator is not that high. Height is not that high. So when you compare these 2 values, in total values, the carbon emission produced by using of elevator is much smaller than those by cars, of course. But actually, these global parameters will apply to this model. But we can actually also classify these parameters according to the types of elevators and cars if you want. And these carbon emission parameters can be reduced, of course, by technological regulation, innovations, and independently of the space configuration. And therefore, we can have finally, for the total amount of carbon emission in a city, this equation is complicated. But the thing is that there are only 2 parts here. One part for vertical part that generates carbon emission, and this is horizontal part, right? Right. Now we are ready for our first simulation, which is about complexity. Here the constant is total floor space remain the same, and also population, and we assume street layout is regular, as shown in this figure, and also building height is also uniform. So it's kind of an envelope city, in which all important thing is density. So density is changing to increase in this way from sport state to compact state. As you can see, as it as it becomes compact, of course the vertical part of the carbon emission increases, of course, but the horizontal part decreases because the city becomes more compact. But there is a kind of the minimum point in the total amount of carbon emission. In this case, here. If we plot these variations of horizontal part and vertical part and total carbon emission amount, then we can have this kind of curve which has a minimum point in it. It is because compactness brings about the increase of vertical part of carbon emission, while horizontal part of carbon emission decreases. So we sum them, there should be some kind of minimum point here, which we call optimal density, which is total amount of carbon emission which is a minimum. But such an optimal value does not always exist. It does not exist when population is not large enough. So this is our case in our simulation. But if we decrease the population, then the carbon emission just decreases continuously without having a minimum point or turning point. So this means that the argument for complexity can regain most of its power only when population the city needed to accommodate is relatively small. If it is too big city, then we can just make the city compact with very high buildings without cost. There is a cost which you have to pay. Right. This is second simulation, and now we are moving beyond complexity. So in this case, constant is still the population and floor space are the same for all these 9 diagrams, and also we assume the population density is also the same. We will start from this uniform distribution or configuration, which, as we have seen in the previous simulation, this is not the optimal for this size of city. But we'd like to see that if we change street layout and building heights, then how far these variations in physical configuration can make the carbon emission amount decrease toward the optimal point. Try. And so, if you look at this way, there are let's say there are column. This row, there are 3 rows in this way, right? Represent the local height intensification in the center. So buildings at the center will have a higher but in this way, if we move from the first column to the third column, we'll see gradient intensified in the center. So there's a kind of line diagram in this matrix, right? And if we calculate the total amount of carbon emission, which is composed of vertical part and horizontal part, you can see this kind of result, which shows that in reference to this uniform distribution, we can have the minimum carbon emission at A1 configuration, which is a kind of height is very building space is very high at the center, but grid is not that dense. Grid is all, more or less sparse in the center. Okay, and because in this case it's not very realistic, we have to see that all these values are increasing compared to this distribution or configuration. So, right, to say that with varying this physical configuration, we can almost achieve the original and optimal arrangement with a higher density in the simulation, in the first simulation we have seen. If we look at carefully those variations, we can summarize the result as in the following. For the height intensification in the center, C to A, we see that horizontal part always tend to decrease, okay, irrespective of local grid conditions. And also, vertical part obviously should decrease as the building gets higher in the center. But for the grid intensification, there is no such clear tendencies here. If we look at the series from 1 to 3, horizontal part of carbon emission tend to increase. For instance, in the case of AX, horizontal part increases from here to here, but it tends to decrease in the case of E's rho. If we see that we are moving from here to here, the carbon emission will increase. Yes. So, question. Are these results at odds with what Hillier argued for local grid intensification in the center? Right? This is the opposite case to what he has shown to us. In Hillier's idea of local grid intensification in the center, distance is on weight, as you know. In our model, this is distance in horizontal movement is weighted by the total floor area by individual buildings. That's the difference, crucial difference. If you consider positively that Hillier's idea of local grid intensification assume that not on weight, but same weight of total floor area, then we can verify that local grid intensification in the center does bring about the decrease in carbon emission. For instance, if you follow this series from C1 to B2 to A3, then the total amount of carbon emission will decrease as it predicted. Nevertheless, the A3 configuration in which both grid and height intensify in the center is far from optimal, as we have shown. This is close to the optimal. It's the best one in this line configuration. So this implies that we need to first distinguish pedestrian grid intensification in the center from vehicular one. Well, because Hillier didn't take into account this distinction, so we are considering only vehicular movement in this model. So for vehicular movement, it is better for the center to be sparse as far as it can. But for the pedestrian movement, it should be dense enough to according to what Hillier suggests. So we can, if we put them together, we can envisage this kind of dual grid network of pedestrian and vehicles. Now I will apply this model to real case study, to the Newtown project in Seoul, where I need to introduce a bit about this project. Initiated by Seoul Metropolitan Government in 2002, Newtown project denotes large-scale urban redevelopment, which aims to systematically reorganize outdated residential quarters and to foster urban core in the undeveloped areas toward a more balanced development. This is not a Newtown suburb, but a town within town concept, which can be typically envisaged as an estate of a high-rise mixed-use buildings that will replace a flat area of a low-rise building, residential building mostly, along with more green areas such as parks and other well-being facilities. You can see much green spaces in here. So this is before the project and then after the project. I know you this morning or yesterday you just passed along this Newtown project area, and particularly this is called Wangxing area, or WS area for short. This is the result of our model. I will show you 5 examples of this Newtown project among 20 or something. I forgot. But this is first example for Wangxing, and this is before and after. Of course, the buildings get higher, the change rate of total flow rate will be increased, but the total amount of carbon emission will decrease by 2.2%. And being less, but more or less the same result we can see for the Yeongdeung area. Before and after, we can see the change rate decreased by 0.8%. The same goes for the area called Dong-E, Newtown, with its smaller change. But in this case, for Karirong Newtown, the total amount of carbon emission increased on the contrary. Well, maybe because it's the case that in this area there are already massive buildings around this site, so can the effect of this development can be tend to be diffused surrounding it. That's what I guess. And for the Cheongho area, this is the worst cases among those 5 samples. It will increase the carbon emission by 0.6%. And this is perhaps because the location of this project area is at the riverside, so that it can have kind of local grid intensification effect in the center. It's kind of more or less similar to the periphery development. Now, in all the 5 samples of Newtown project, we can find that carbon emission potential for individual buildings is directly proportional to their total floor areas, as we can see in this graph, scatter graph, before and after for Wangxing development. This is total floor space for individual building, and this is carbon emission per capita for individual building, which I call carbon emission potential. And it can be summarized as this simple equation. The regression equation has been set to have the origin, and we can see the intercept part here. And it can be set like this or this. So the total amount is just proportional to the total amount of the floor space area. What I suggest is actually, well, at first rule, we can see that, well, this is pretty much obvious fact. As total floor space increase, the population will increase, and it will make carbon emission amount will increase as well. But as we have seen in the previous example, there is some cases in which carbon emission decrease, even though there is a clear dependent relation between these two variables. Then what happened? Actually, total amount of carbon emission may decrease while the sum of the total floor area increases after development, which is only because the parameter here and here, here, changes along with the development. So what I'm saying is that it is the parameter mu that is by nature characteristic of the spatial configuration of building height and street layout. All the information is hidden in this parameter. Okay, so we can say that not only that the carbon emission is proportional to the size of buildings, but also that total amount of carbon emission is affected by the configuration of those buildings and the street network. Now, conclusion. How many? It's over, right? Based on space configuration model to estimate carbon emission, this paper has located what can be discussed further within the current discussion on complexity. And however, the model can be made more realistic by taking into account building usages and lifestyle, residence, so on. And the implication of the result may be interpreted differently depending on the scale of areas under analysis. So the central part is large, that's good for vehicle movement. But how large it is? If it is too large, it will be difficult for pedestrians to move around. And we need to develop a way to calibrate carbon emission amount which this model estimates relative to real amount observed with the vehicle and elevator movements. But it's very difficult to apply data, real data. And we also need to overcome computation costs. Currently, this model is based on UNA ArcGIS extension. Probably you know that, made by, do you pronounce this name? So, well, okay. In my experience, it takes roughly about 10 hours to compute to 20,000 buildings. So if we need to broaden the area in which this model can apply, then we need some different platform or supercomputer or something. That's it. Thank you.
Yes. So in the specific term, sometimes the complexity is talking with the comparison between local and global. So in other words, maybe synergy, something that are clear between the local distribution and the global distribution.
Does it imply compactness?
It's we know some I think Denmark researcher, and also at the same time yes, big user.
All right.
It's irrational if you use that how to say distribution between compact local. So I think that's the, your point is very interesting. And you make the center too strong. It's not compact. But that distribution, a little bit some balance, then carbon is now the minimum. So in the case of might be some building could be calculated within the several values and compare. Then I think that something that we can find some reason why the good balance distribution is less carbon.
Yes.
So did you think about how?
To be honest, I haven't think of a local distinction in this model, but I'll think about your comments. Yes.
Just to comment on the finding that the larger block in the centre had a lower thing, because you could divide that up and make a pedestrian-only zone, and then you wouldn't have any carbon emissions from the cars. So you could actually have greater intensification. You do find from just anecdotal experience in the central cities, find smaller, denser roads which are only populated by pedestrians and not by cars. And then the cars will go along, say in syntax terms, the high choice routes, and then the really small, dense areas are actually mainly pedestrian flows. So you might actually find if you say weighted the proportion of carbon emission by between the centrality, you might actually find that you can have very high density, small blocks in the centre which are populated by pedestrians, and actually still have the lower carbon emission possibly.
That looks promising very much. Yes. I'll try that.
Thank you. Very interesting model. I have a question regarding an issue that bothers me with this concept of the compact city and all these models and methods to evaluate them, which is the boundary. The boundary in terms of putting a limit around the development and looking in. You mentioned the point there where you said, the result of this one is a bit surprising and not so good because it actually is adjacent to already existing areas.
Yes.
And to me, any kind of evaluation that just cuts off and measures in will never be able to capture the real effect. Because even a densification on a corner, if it becomes a shared center of an adjacent neighborhood, is a totally different thing from this same densification on a corner in an isolated area. So it's more of an open question than a challenge. How do we make this almost a shifting boundary, or even not use boundary, to define these things? And I think that one of the things that plays in that's interesting is to the point density. So density is measured, and these features are measured at every point rather than within an area. So this is an open question and a challenge. How we can measure these things without having to limit it.
Sure. That's really difficult. In our cases, I have applied 4-kilometer circle around the Newtown project area, but it's highly artificial, of course. And also the carbon emission amount will be dependent on how big the area is. Actually, we try to apply this model to the more or less small or middle-sized city because in that case we don't have this kind of problem of defining boundaries. But the problem is that for the middle or small-sized towns, it's really difficult to get height data or whatever data there are. So that's why we choose to apply this model to more large cases. But it is to it's highly critical how we define boundaries for this kind of research. Yes. Yep.
I think I thought it was a very interesting presentation, but I was thinking about what you actually say is that if you concentrate your floor space in the center, that's a good thing if you want to reduce carbon emissions to a certain extent, let's say. But the fact and it has to do with let's say that you stop measuring at a certain level. Let's say you define your areas, because it might be so that another distribution has a potential to facilitate more floor space than another solution. So if you, so it might be the case that if you would take the whole city into account, that the choice for a certain solution means that you have to grow further out, let's say, in the territory. So I think that needs to be included somehow, and it has, yeah. Though it's tough, but I think there are some ways. It's very interesting.
That's it. Want to take your